Okay, so let us try next part. So now we have seen how to do Gram-Schmidt. Let us now look at another question, which is how to take projections. So suppose I have given you a vector B, in terms of V is some span of B, okay, where B is U1 to UK. Okay, so we did projections already when we did A transpose A inverse A transpose B, that we did already, but I would like to now show you like if this U1 to UK are orthonormal, how does the projection look. Okay, so what we will do is suppose each of the UIs are belonging to RD. So I have k vectors, naturally k is less than d. So what you can do is you can extend the basis. So you take B bar, which is equal to U1 to UK, and you add vectors UK plus 1, UK plus 2 all the way till UD, d dimensional. Okay, so this you can make it. So d dimensional, n dimensional, I may keep changing d and r, but please don't get confused, and such that B bar is still orthonormal. So the way we do it is you take any vector other than U1 to UK which is linearly independent, and that vector you apply Gram-Schmidt and you can generate this. Okay, I hope this idea is clear. So now what is projection? So basically we call XP projection of a vector V, XP V is of a vector X. Okay, so that is equal to arg min X bar belonging to V, okay, length of X minus X bar square. So you have some subspace, okay, this is the V subspace, and then you have a vector which is not lying in the subspace. What you would like to do is you would like to come up with this projection. Okay, so this projection I am calling it as XP, XPV. Okay, so that's the goal, and this vector is vector X, and this projection is whatever minimizes this error. So X minus X is this error, so I want to minimize the length of this error. Okay, I hope the geometry is clear. Now how does one find it? So the claim is XPV is summation I going from 1 to k. Note it goes up to k only. Okay, X UI UI. Okay, so it's very elegant. You are only looking at this. So this belongs to naturally is a vector in V. Okay, so how do we check it? So let us see. So so we can obviously do this. So any vector X can be written in terms of the basis B bar as follows, right? So I can write this as X UI UI I going from 1 to k, then other elements which are not there in the basis B but in B bar, I going from k plus 1 to d X UI UI. Okay, now if you take any vector X per X dash in belonging to V, you can write therefore X dash will be some beta I UI I going from 1 to k. Okay, so if you look at X minus X bar square, right, you remember I told you if there is a vector alpha, beta, gamma in R3, length of this vector is alpha square plus beta square plus gamma square. So same way the length here will be summation I going from 1 to n beta I minus X UI square plus this not to n to k, and then I going from k plus 1 to d X UI UI. Okay, so sorry, this UI is not there, this inner product square. I hope this is all right. Now if you see any vector x bar I can take, I can never control this part of the error. The only thing I can do is control this part of the error. Therefore beta I must be equal to x ui to reduce the error to. So hence we have proved the claim. Okay, so this is one thing that I wanted to say. Okay, all right. So now now that we know this, so what are we trying to do? We are trying to solve what is called as maybe I'll take a break here as well.